Okay, so this is the final video in our logarithms topic, and here we want to look at returning to exponential equations, which we looked at the beginning of the topic, but now looking at how we can utilize logarithms to help us solve exponential equations. So as I said, we've already met exponential equations, and we know that we solve exponential equations by trying to write both sides of the equation as a single power with the same base. So for example, if we had this exponential equation here, all of these things can be written as powers of 2, and so we focus on doing that first, and then we make sure that we have just a single power of 2 on each side of the equation by using our index laws, and then at that point we can equate the powers and say that x plus 2 must be equal to -1, and so therefore x is equal to -3. This is still our preferred method. If you can express everything in the equation as a single power, with the same base, then we want to try and, that would be the best way to solve the equation. However, if we cannot express both sides of the equation with as a power with the same base, then we need to use logs. So for example, an equation as simple as 2 to the power of x equals 5 cannot be solved by trying to write both sides with the same base, because 5 is not a power of 2. And so in these instances, we must use logs to solve the equation. Now, there are two different ways to solve an exponential equation using logarithms, and in most instances you'll use method 1. Method 2 is actually a method that's a bit of a hangover from a time when calculators could only deal with logs with a base of 10 or base of e, which is something we'll talk about later on, but base 10 let's stick with for now. So what that meant is if you wanted to solve an equation, or if you wanted to do anything, you always wanted to try and use log with a base of 10. And so therefore, getting an answer that was log base 2 wasn't very helpful, because you actually couldn't then work out, a decimal approximation for that. So we always used a base of 10. So this method still hangs around in a lot of teaching in terms of, it being the way to solve these equations. However, I would use method 1 in this particular instance. What I do want to say though is there are times when using method 2, which is to take log of both sides of the equation, is a useful thing to do, and we'll look at an example where that happens. So if we did method 1, which is making use of this relationship, which the whole topic really has centered around. If a to the power of x is equal to y, then x equals log base a of, that's an error, x equals log base a of y. And so therefore, if 2 to the power of x equals 5, simply using this exact relationship, log base 2 of 5 is equal to x. So the base of the exponent becomes the base of the log, and the other two things pretty much switch sides. Okay. The other method is to take log of any base, whatever base you want to use, a base of your choosing of both sides of the equation. So if we do that here, so in this example, I've done what we would have had to do when we were limited to only using base 10 logs, which was to take log base 10 of both sides of the equation. And the advantage of that is that if you take a log of an exponential, we know that our log laws allow us to bring the power down to the front. So this is how we free the unknown, in this case x, out of the power of the exponent so that we can solve. So we get x times log base 10 of 2 equals log base 10 of 5, and then we can divide, because this is, remember, this is just x times log base 10 of 2, so we can divide by log base 10 of 2 to find that x is equal to log base 10 of 5 over log base 10 of 2. Now, what you'll see is the two different methods gave us two very different looking answers. However, if we type those into our calculator, we see that they do still give the same value. They actually mean the same thing. So what we're actually seeing here is log base 2 of 5 is equal to log base 10 of 5 over log base 10 of 2. And that would be also true. We could have chosen any base. We could have chosen to use log base 23 if we wanted. And if I show you here, sorry, my apologies, let's fix that. If I instead had done it with log base, what did I say, 23. So if I did log base 23 of 5 over log base 23 of 2, and press Control Enter to get a decimal, that would also give us the same answer. So you can choose whatever base you want if you're doing the taking log of both sides method. And in fact, that's kind of what's happening magically in this step here. What we're actually doing is taking log base 2 of both sides. We're taking log base 2 of 2 to the power of x equals log base 2 of 5, and the x can then come down the front, and so we have x times log base 2 of 2 equals log base 2 of 5, but log base 2 of 2 is 1, and so that's just x equals log base 2 of 5. So it is what we're actually doing in that step. We're actually taking log base 2 of both sides of the equation. So both methods work. This idea that we see here, the fact that these are actually equal to the same thing, can be generalized actually into a rule. So log base A of B, for example, is going to be equal to log of any base, whatever you choose, of B over log of any base of A. We call this the change of base rule. We won't explicitly cover that this year, but it comes up incidentally because you can get different looking answers depending on the method you choose to use it. So if when you're working through these problems, as you're doing your exercise work, if your answer doesn't match what it says in the answers, press Control Enter to approximate your answer as a decimal, just so that you can check that your answer is still correct. I think from memory, the answers on the worksheet that I've set for you, I've given an exact answer, but I've also then given the decimal approximation so that you can compare your answer, just in case you've also got a correct exact answer. Your answer should still be given exactly involving the logarithms, but I'm just giving you a way by which you can check that your answer is correct. Okay, let's work through some examples. So solve each of the following for x. So in the first example, 3 to the power of x equals 14. I would simply convert this directly into a log equation. So the base of the log is the base of the exponential, and then the x goes into the log, and the the other way around. We free the x is coming out of the so it was in the, if the x is in the exponential, it doesn't go into the log. It's the thing that you're freeing out to be on its own, which is what I mean by the other two things switch sides. So x would be equal to log base 3 of 14. And again, our understanding of logs is 3 to the power of what gives me 14. So 3 to the power of x equals 14. It's the same thing. Okay, question 2, I would do the same thing. So I would convert this from an exponential expression into a log expression. So this is going to be that x plus 3 is equal to log base 5 of 22. And so therefore x is equal to log base 5 of 22, take away 3. Now you can stop at that point. There is absolutely nothing wrong with that. If you want though, you could focus on trying to write your answer as a single log. So log base 5 of 22 minus 3 times log base 5 of 5. The 3 can go up into the power, because log base 5 of 5 is 1, remember. 3 can go up into the power, so we get log base 5 of 22 minus log base 5 of 5 cubed, which is 125. We're subtracting logs, and so this is the same as log base 5 of 22 on 125. That isn't to say this is perfectly correct up here, you've answered the question, but this is also the same thing. Alright, question 3. 5 times 3 to the power of x plus 1 equals 10. Now, the common error you'll make here is you'll tell me that that's the same as 15 times x to the power of 1. Now remember, that's not how indices work. You cannot just multiply the bases together and expect it still to be the same thing. Let me give you an example. If you have 2 times 3 squared, well that's 2 times 9, which is 18. It does not equal, it doesn't equal 6 to the power of 2, which would be 36. So you cannot just multiply the bases together. Okay, remember, order of operations, the power happens before the multiplication. And so therefore, you have to be able to deal with this in a different way. In fact, the easiest way here is to just divide both sides by 5. So this is actually 3 to the power of x plus 1 equals 2. Okay, so then we can convert to a exponential equation, log equation. So x plus 1 is equal to log base 3 of 2. And so x is equal to log base 3 of 2, take away 1. Now again, I might try to combine those together. So that is log base 3 of 2, take away 1 is log base 3 of 3. And so this is log base 3 of 2/3. We're subtracting logs, so we divide. Again, this is correct, you've answered the question here. This is also the same thing. Alright, question 4 I want to have a look at. This is a different example, and this is different and harder because we have unknowns in both powers. So if I were to convert this to a log, using a log with a base of 2, I would get x equals log base 2 of 7 to the power of x minus 1. Now that's going to work. But I'm going to have to do quite a bit of work because I've still got my x now trapped in both in a power and in a log. However, we can bring that down the front. You could also do it with the log base 7 instead. So you could say, well, log base 7 of 2 to the power of x is equal to x minus 1, and then go from there. Okay. You might also find it easier. I tend to find it a bit more confusing to make the switch like that with these. I tend to find it easier to think about taking log of both sides in this case. And again, you can choose whether you take log base 2 of both sides or log base 7 of both sides. Whilst 2 is a nicer number, it's often, it is sometimes easier to take the to use the base of the more complicated exponent. Okay, so I'm going to try and take log base 7 of both sides here. So log base 7 of 2 to the power of x is equal to log base 7 of 7 to the power of x minus 1. Okay, so then what I can do now is, in taking the logs of both sides, it allows me to bring the powers down to the front. So we now have x times log base 7 of 2 equals x minus 1 times log base 7 of 7. Now log base 7 of 7 is 1, so we actually have x times log base 7 of 2 equals x minus 1. Okay, so now my next problem is we've got two x's in two different places, which is what we had happening in one of the examples in the previous video. We had a very similar, the question started at this point. Okay, so the key is to get the x terms on the same side. So what I might actually do is I might, which way around am I going to do it? I think I might add 1 and subtract x times log base 7 of 2. I might do it that way around. It isn't to say you couldn't have the equation as x times log base 7 of 2 minus x equals negative 1. I just didn't really want the negative 1. So I wrote it this way around. Okay, so then we focus on taking out x as a common factor. That's how we're going to be able to collect like terms when we've got an expression like this. Now again, I might want to focus on getting this together as a single log, or I might just leave it as it is and divide like that. So essentially now we've just got x is being multiplied by 1 minus log base 7 of 2, and 1 minus log base 7 of 2 is just a number, so we just want to divide by the number to solve for x. So x will be equal to 1 divided by 1 minus log base 7 of 2. I'm perfectly happy with that as an answer. Now if you want, you could focus on combining together because 1 is log base 7 of 7, take away log base 7 of 2, and so it is the same as log base 7 of 7 divided by 2, and so this is the same as 1 on log base 7 of 7 on 2. I don't love fractions in fractions though, so I might leave it as the first one, but I'm happy with this as your answer at this point. There are also different ways that answer could be written depending on how you did the rearrangement of the equation. The other thing is you might have chosen right back at the beginning to take log base 2 of both sides. Log base 2 of 2 to the power of x equals log base 2 of 7 to the power of x minus 1. And then again, you would have ended up with a very different expression. So just making sure that you can check that whatever expression you get, your answer is still, the decimal approximation, it's still equal to the same value, okay? So that's why, as I said, I've provided the decimal approximations for you in the answers on the worksheet, not because I want you to give decimal answers unless it tells you to, but I just want you to be able to check that your answer, if you've done it differently to how the solutions did the answers, that your answer is still a correct answer. So the work here is on a worksheet using logarithms to solve exponential equations.